Hi. I can see the audience tonight, so I can see also from the size of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept. I published the title of the talk in clear and precise language and didn't make it sound like it was something it wasn't. It's the relation of physics and mathematics, and if you find that in some spots it assumes some minor knowledge of physics or mathematics, I cannot help it. It was named... In thinking of the applications of mathematics to physics, it's perfectly natural that mathematics will be useful when large numbers are involved in complex situations. Although, for example, if we took biology, the action of a virus on a bacterium is, if you watch it under the microscope, unmathematical. A jiggling virus finds some spot on this odd-shaped bacterium, and they're all different shapes, and finds some spot, and maybe it pushes its DNA in, and maybe it doesn't, and so forth. And yet, if we do the experiment with millions and billions of bacteria and viruses, then we can learn a great deal about the viruses by taking averages and working with large numbers. And we can use the mathematics involved in the averaging. We can see whether the viruses develop in the bacteria some new strains and in what percentage, and so we can study the genetics, the mutation, and so forth. To take another more trivial example, you know, imagine an enormous board, a checkerboard to play checkers, or drafts. And if the board is very large, the actual operation of any one step is not mathematical. It's very simple if it's mathematical at all. It either goes one side or the other on a diagonal, or it reaches and becomes a king and can go backwards when it reaches the end. In other words, the statement of the rules are very simple and do not really involve any mathematics. But you could imagine that on an enormous board with lots and lots of pieces, some analysis of the best move or good moves or bad moves might be made by a deep kind of reasoning which would involve somebody having gone off first and thought about it in great depth, and that becomes mathematics, this abstract reasoning. Another example is switching in computers. If you have one switch is either on or off, and there's nothing very mathematical about that, although mathematicians like to start there with their mathematics. But with all the interconnections and wires to figure out what a very large system will do, one requires a mathematics. And I would like immediately to say that a mathematics has its primary application, or it has a tremendous application in physics, in a discussion of the detailed phenomena in complicated situations, granting the fundamental rules of the game. And that is something which, if I were talking only about the relation of mathematics and physics, I would spend most of my time discussing. But since this is part of a series of lectures on the character of physical law, I do not have the time to discuss the applications of mathematics and physics to calculating what happens in complicated situations, but we'll go immediately to another question, which is the character of the fundamental law. If we go back to our checker game, the fundamental laws are the rules